Hello, my fellow programmers. Welcome back once more to this Animator PLC course. And today we're going to analyze the different types of data within our PLC. And we're going to analyze examples. Now let's get to it. Now, as you remember, we analyzed our input and output devices. However, we've only analyzed sensors or activations for zeros and ones. So this means that I'm either detecting something or not detecting anything at all. I'm either activating my motor or it's on or off. Now, what would happen if I wanted to get a reading for our sensor? So specifically talking about programming for ladder diagram. As we know, we're talking about normally open and normally closed coils. So if we want to get the reading and for example, I run a drill. Let's suppose that I have my normally closed contact and I want to direct this towards, let's say that I want to direct it to my temperature sensor. But remember that this contact can only allow zeros and ones. I'm either on or off. So this can't result with my thermocoupling for temperature because it doesn't only have a 1, but it can get to 2 or 3. It can even get to 5 or 10, depending on how it's reading my sensor. So for my contact, we're going to get an error message because it's saying that it's not possible to select that input, which is actually analog, and we can't read it. So for this, we need to learn how to identify the different data types. In the case of inputs with only one value, we know these as Boolean. Okay. In Spanish, we know these as booleano. But we also know these as BOL or bool or bool. If we see bool, this means Boolean. And this means that it's only uh, a data type that can only take zeros or ones. Now, what type of data is a device that more than it handling zeros and ones, it needs to be greater. So here it can take 2, it can also take 5, it can also take 30, okay? And if this is closed data, like 30.0 or a 25 or 29, if it doesn't have a decimal point, but it's larger than 1, then these are known as integrals or integers or ints. And we can also use dint, which is double integers. Okay, so I'm going to explain this a little better. If we don't need a decimal, if in this case, this sensor is not only going to send like closed numbers, non-decimal numbers, because temperature has decimal points. So it can be 29.5 degrees or Celsius, or it can send it out to 22.5 Celsius. If it's higher temperatures, let's say, for example, 55.15, okay? So this is in general. We know that we can also run in scaling, but these examples are for us to understand better. So these are for decimals. for this reading or this writing. And then we're going to use a data type, which is real. Okay? So let's recap. If we use zeros and ones, this is Boolean. If we use more than zeros and ones, and we're not going to be using decimal points, we're going to use whole data or double integers. And if we use decimals, they're going to be real data. Now, let's see if this is true. I'm going to ask you guys, what type of data is this device going to be? We said it's Boolean, and this data type is a thermocouple, okay, a thermocoupling, and this makes it real. So sensors, zeros and ones for a data type. For a button, it's either on or off, but I can stop this, zeros and ones, Boolean. Selector, I'm either activated or deactivated, zeros and ones. Boolean, the encoder, there are some encoders that if you read or assign data without decimals, then these would be double integers. If we need more precise data, this would be real data type, which this would also make it a sensor and Boolean. Okay? Now, we already identified our inputs. Now, I'm doing this to make this much simpler. I'm trying to innovate this explanation. So you guys tell me what's the, if you're understanding the explanation, leave it in the comments. Now, outputs. This is a lamp. I'm either on or off. It's a Boolean type. So inputs and outputs, they have data types, and we need to learn how to identify them. That's very important, guys. So Boolean, which are these? These are coils. We can send certain voltage, or these are generally voltage, but then we would send it from 0 to 10 volts, or 2 milliamps, or 4 MPs, depending on the output type that we have for our PLC, or whatever output that is sending for our coil. So generally, these are real data types. When they're analog, they're generally real. Now, this is a servo motor. Now, what are we going to send? Also voltage, or we're going to send position signals. If these are positions and they're more exact, then this is going to be real data type. For induction motors, start and stop, and for real data type. But if we assign a speed and we wish to gradually keep that velocity, in this case hertz, it could be RPMs, depending on the application, what data type would we need? If it's decimal, then these would be real because hertz we can send, for example, 15.4 hertz or 5.4 hertz as well. But the goal is going to be decimal. Okay? Now, pistons. They can be either cylindrical or valves. If these are pistons with motion control or position, or for example, uh, proportional valves, these can also be real data. Or if we only activate our piston so that it is either totally open or totally closed or completely extended and contracted. So zeros and ones. So what type of data is this? This would be Boolean. So as I said, there are certain devices where instead of them being the whole shaft out, it would be only half of it. So these are very similar to servo motors or cylinders or pistons. So it all depends. And then we have our relays, which is zeros and ones, which is the one that is used for our output. So then that would make it Boolean. So thank you guys for following me with these examples. Now, this is the more technical part, which is simple also. What we had previously said, a Boolean or a Boolean data type has a 1 bit length. Now, what is a bit? Boolean, if we open this chart, it can only take 1 bit at a time, 0 and 1. So 1 bit. Now, in my data type, which is a byte in this case, or a simple integer, its compound is 8 bits. Now, I'm going to explain this to you guys, but I'm also going to summarize it. A different data type is either one word or whole integers. So Siemens uses word and integer. So for Allen Bradley, if you have a word internally, but in reality, Allen Bradley uses only int and sint. So Allen Bradley went a little bit more for PLC programming, which I'm going to explain in a little bit. And these are 16 bits. Okay. Now an integer has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 what? Boolean data types. 16. Oh, well, you know what, Rodrigo? I'm counting here from PLC programming. So for PLC programming and IT, we start from 0 from our first value. Not for everything, but for our chassis or our rack for our PLCs, generally our slot starts from slot 0, 1, 2 because of the same thing. However, if we were to add from int point 0 or point 15, it's going to be 15 bits total. Now, 1 byte, as it says here, what does it match? 8 bits. One Boolean, let's suppose, is 1 bit. So if we break it down, because I love how Allen Bradley has this structured, and this is how our concepts are clearer. So byte. We extend this data type, and it's going to be a series of how many booleans? 1, 2, 3, 4, 5, 6, 7, 8, from 0 to 7. So these are 8 bits total. So a boolean, how many bits does it have? 1. And here we can't really deploy it because it only has 1 bit. So a double integer, as its name states, it's a double integer. So if one integer has 16 bits, double is 32 bits. So this is the plus sign. And if we open all of this, then it's going to be 32 Boolean data types. And a real data type, we can't really deploy it as double integers, but internally, they're actually structured so that we can get our decimal values. And internally, our programmers have a 32-bit length. But our software companies indicate that this is real data, and we know that this is a 32-bit length. And especially for our length, what good does this do to us? If you notice what I said at the beginning, This is for us to be able to receive our information or our ranges, because the bigger the Boolean is in our data type, that means that we're going to be able to use for our program or read or have certain readings, in this case, temperature sensors with certain range. So then we can be able to read with it through this reading our bit length so that we know what's the top and the bottom. Or in this case, I'm going to analyze this. Or in this case, if it's only a sensor, then we don't really need it to analyze all this type of data because I need to know if it's on or off. So then it's important for us to know the data type so that we really know how to optimize our PLC memory, because if we remember, our PLC already exists. So we already, cracked our head trying to identify our inputs and our outputs, but we should be able to know what our program already left in our manual or for our PLC so that when we implement, we can tie it all together. Now, a pulse. What type of data is this? It is a Boolean. And now, what type of data is this? A selector. So Boolean, so temperature sensor, real, encoder. Sometimes they read double integers, or generally even, they read decimal points. Because for motion control, to prove the point, especially for the data type, in general, we run this software. And remember that this is only to reinforce our knowledge and to set as an example for what we've seen, especially for the data type, which this is why I love Adam Bradley to explain, because it's very similar, but at the same time, we can understand the concept. Okay? So we have here a very small exercise, which is the pneumatic box, which is for the same point if I wish to add or assign a direction to my input or my normally open contact, then here I should be able to add a memory. Now, memories, I'm going to analyze them based on class. Now, this is very simple, guys. So then we need to assign a name to that memory. And let's set it out as input name, which is 1. And here, guys, this is where we need to understand our data type, which indicates when we create a memory, what type of data this is, which in this case, it's a Boolean. So if it's a Boolean, it's indicating that it's telling me that everything is okay. So it matches with that data type, which in this case is a Boolean. Now here we compile it, and here it's being generated by our PLC. Now, there's a part that says controller tags, which complies for our physical or virtual memories. Now, for controller tags, we can start checking our memories that we had created. For example, if we create here a memory, which is called ball or boolean, remember, one thing is the name, and something completely different is a data type. Perfect then. Now here it states a 0 and 1. So 1 is received, but what would happen if it changes to a 2? So the program is not going to allow me to do so. So there's going to be a flaw, a failure in the data type. So if you're telling me that this is a Boolean, I can't assign a number 2. I really can't. So physically, I would have to be programmed to not accept any data type. So perfect. So then we would move on to our famous synth or our simple integer. Now, how many bits does one whole have? 16 bits. Now, why do I say in PLC? Because there's also the data type, which is integer. And I'm specifying this because further down, in case you see this uh, data type in IT, but it's not 16 bits for IT. For this, it is worth 32 bits for them. So PLC 16 bits, one integer, and IT 32 bits. And for those of you who are studying IT or programming, okay, don't get scared, guys. This is a a subject that is kind of an iffy subject. Because if we analyze for our software, not only for other animations that we've done. So in a PLC, one integer is worth 16 bits. So an integer is half of an integer for a PLC. Okay, this is the last time that I say this, guys. I promise. I just want to say this so that there's no further confusion. Okay, so I'm not going to confuse you guys anymore. And then we run for the integer for this course. It means that these are 16 bits. Okay, now simple integer. How many booleans do they have? Half of 16 is 8 bits in theory. Now, let's see if this is true. Where is it going to start from? From 0 to 7. So we create the memory. One thing is to create the name, and the other completely different is to create the data. And we create it, and now we see, instead of more or less, an arrow, or yeah, an arrow. And now it's deploying a suit menu, which in a submenu, which in this case is submemories within our simple integer. It is composed of more booleans. That's the incredible bit on this. So then a simple integer, what does it support? It can support a 2, or a simple integer can also support a 5. Or a simple integer also can take up to 9. And if you notice, on the bottom part, the booleans start playing with our tables or our charts. So if we analyze them carefully, they're really very easy. Okay, so they can start running PLC exercises or drills. But again, these are so simple that I consider them that this is also very simple and easy to learn. Now, what happened when I added a value for a range which is above the indication? Then I would say, well, now you're going over the line. So it's giving me that there's a problem. So I'm adding 222 and it's not allowing me to do so. So on the bottom part, it's activating 1, 0, 0, 1. They're playing their game. Okay. So this type, zero, ones, and these combinations, I wouldn't want you guys to memorize them, but I actually want you guys to analyze the real part. As we can see, Boolean 1, 0 point, and that's where we start identifying each one of the Booleans. This is done automatically with syn.0, syn.1, and all the way through syn.7. If I were to add for all these data, for all these values, it's going to indicate -1. Now, this is in case that it's already foreseen the PLC. But if I indicate all the booleans in 1, I'm going to get in total, it's going to tell me, well, I can only show you all the way to -1. The real value, which supports our PLC, in theory, would be 128. Sorry, 127. If I add 128, one more data, it would indicate that it's not possible. So then what do we do? Well, for this, we have our very famous integer. So if we create a name, data type, and we create a deployment 000, perfect, from 0 to 15, the theory would make sense. So here's now allowing me to do 128 with a simple integer, but my double integer would allow me to do so. Why? Because I'm seeing that it's indicating me here something. I have 1, a 0, I have a 0 here, another one, another one, another one. It should show me 128, but internally in our memory for simple integer is not allowing me to do so. It's from 0 to 127. So this limit would also have certain exponentials. So we're going to be very practical about this. So 127 is its limit. Now, what is the limit for our integer? We can continue testing this if you wish. So let's add 999, 9,999, and it's not allowing me to do so until 9,999. Let's see what's our limit. If we add them all the way to 1, I can't add more than 2 because it's going to give me an error message. So let's brand them as 1, 1, 1. And our last data is not going to allow me to do so because it's going to give me a negative. So it's going to be -1. So from a max value to minimum value, we're going to assign and we're going to fill all of them to 0.14. This is max limit, if you can see, guys. The more booleans we have, the more we're going to be able to use them to read and to get readings, or to write down to send information to our output devices. Now we need more. Okay, perfect. So then we're going to add more. Double integer. And this is for the data type. From where to where? From our Boolean, from our dint.0 to dint.31. Okay. So from 0, which this is already bigger, to our 31. So in theory, it works. What number is it not allowing me to? 9,999. Here it is allowing me to do so. Now, if I want 9,999, it's allowing me to do so. Sorry, 99,999. Now I would be able to use our integer for our double integer memory, and I would assign it to my input for a Boolean type. Now I would be able to do so, and it's indicating me an error. And you may say, well, Rodrigo, you can't really directly add that data type, at least not for an instruction. In this case, it would be a Boolean instruction, so you can't do it. But maybe I would be able to do it, and I could be able to use this data type for our limit. That could be done. Now, if your logic tells you, and you can analyze, and if we say, well, if the double integer is a mix of 32 booleans from 0 to 31, it's dosed out for internal memory, then we would be able to use it, right? And yes, however, we would need to direct it. Okay, so we need to add a boolean, 0.0, and that's it. We're now able to use a part of that double integer. But that's the point that we need for one boolean, and we can do this. Now, we might be able to use a boolean for an instruction for 0.0 where we need a larger range. Okay? But in this case, we do need to use a double integer or an integer or a simple integer. Okay? And we need just one more data type. Now, what's next? If we want a bigger data for some reason, there's something else also called link. But we might start needing bigger ranges. So depending on what we use, in this case, a simple integer can be able to help us out. Now, why? Because its range only reaches 127. So the waves, it's from 0 to 24. So we would be able to use a simple integer. Now, why do we need to correctly identify the data type in our memory? To save memory storage. So controller tag, we go to our memories. And this memory that I already created, and instead of me creating a memory, and I can only use this part, only this part, but what's going to happen here? I'm not really going to use it. Now, this situation type is the one that we, right from the beginning, are going to use to optimize. And we're going to see if we really use an integer or a simple integer, or if we need a double integer. But what's the range going to be? If I use, for example, 24, I can use a simple integer because it's 0 to 24. But if I use days and I want to calculate 0 to 365, this goes over. Now, what would I need then? An integer or a double integer. Okay, do you see the difference? So what data type is necessary for this? A real data type. So we need to make them match. So as I was saying, we know that it works with 32 bits, but the internal program is chosen so that we can support the decimals. So here it exists a Boolean 1 or Boolean 2, but no, because it doesn't get decimal points. So if I add here, if I say Boolean at 1.5, it's going to tell me it's not, you can't do it. If I add 0.5, it's not going to support it. So then logically, or for our Boolean, it's not going to accept this. But for our real data here, when we want to add a memory for a data type, for a real data type, our program already cracked its head. And we needed to read or send out information for a decimal point. So 1.5 if it allows me to do so. Okay, so 99.6, it is allowing me to do so. Now I can use a real data type, and I can use real numbers, no decimal points, but it's going to show up as 0.0. Okay, so 9,999.46. It is also allowing me to do so. Can I add more decimals? According to the precision that you require. Now here, it requires all the way up to 3. But you can use more decimals even. So what do you guys think? We already saw Boolean, integer, simple integer, double integer. Now, this is for us to really understand it quickly or simply. Now we can analyze this data type. And if you're ready, let's go there. All right, so we're back to our PLC Animator to analyze all our data type. For our PLC Animator, we got something similar for our data type assignment. However, in reality, they're already assigned. For example, our inputs or our inputs, we can actually analyze if they're selected on our top part, our I for that file, and we can analyze that these are Boolean. And here, for example, we have our final value, which is something very similar that we saw in Rockwell. So we have input, we have output, we have analog input, okay? And all of our analog input, we're gonna view them. Analog output, and these are real data types. That's why we have decimal points. So F. The file is floating, but there's also a real data type. Floating memory, but it's real data type. Same as input, analog input and output. So B is virtual memory. So if I, for example, this could work as input or output. And I was going to explain this more in detail for our next class, but as its name says, these are memories that we can add so that they can run certain functions to simulate certain things within our algorithm. And it's very interesting topics are binary files or virtual memories. So if I select my Boolean and I assign a 1, my value is going to change. It's going to give me a 0. But if I select this direction, which is B semicolon 0.11, and I add a 1, then the value here is going to change. If I add it on 14, I add a 1, it's still going to change. So in this case, it's going to be 18,433, which means it's a double integer. Sorry, or double integer. Which one would it have taken? It's an integer. Okay, so we can start playing around with this. Or for example, if I had a 544, this is a difference between our memory because this memory, even though it's an integer memory, let's add here, for example, 99, it's going to change similarly for our booleans, which comprise of this integer, as we saw in Allen Bradley. And it's going to add according to our programmer, because he already knows what to use according to all the memories. Okay, so this is done through all of our developers. So basically, this is how two different data types work. Now, further down, we're going to analyze that there are analog memories for input as well as for output. So input, output, and we have some really good drills up ahead. So we need to be like really applied. So they seem very simple, but as we move along, they're going to get more and more complex. Okay? So here, for example, we have an output, an analog output, and it is directing to our 0. Okay? So then it's already indicating us what label we need to use. So here we have our analog input, which is a percentage. I haven't really seen our exercise, our drill, but we're going to look at this in the future, in the near future. So we're going to be able to solve all of this, guys, okay? And we're going to improve on all of this. So we have here analog input. And what data type is this? These are real data types. For example, if we can add less, and here we can add a file type, analog input, 0, 0 here. And here we can compare with a 34, for example. Okay. So perfect. Now, we're going to solve this down the line. Okay. So these are decimals, and we're going to get these data types. Okay, let's see, AO. And these are also decimals. So if I add here that this analog output is 0 and that it has a value, let's say that we can save, okay, a 2.2. So we can get the data and we can simulate the data. But that file, that memory file already has assigned that data type, which is a real number. So we already established these types of links for that memory. So without further ado, let's analyze our physical memories and our virtual memories. It's something very simple, but it's actually the basis, the foundation. And many students have thanked us for explaining it this way, for this type of physical memories and virtual memories, because it didn't really exist as a comparing point. Or it did exist, but they were called logic memories or physical memories or something. But we don't want to cause more confusion. We only want it to indicate as programmers. Okay, so let's go there. And then that's where we start getting a little bit more explanation topics. And then all the way to the end, you guys can decide if you want to head out to the Animator PLC so you can learn how to use them, which we can start gravitating towards, or the exercise selection. So you guys, you say what you want. Okay. And then you guys can be with us with our basic instructions, our intermediate instructions, and then our advanced instructions. So congratulations, guys, for getting to this point. And let's move on, guys. Thank you very much for your time, and I'll see you in our next class. Big hug.